two phenomena called burst drug release as well as the sustained or the controlled drug release. Okay. So look here, the x-axis is time and y is how much the drug was released actually, percentage. Okay. And this may be a quantitative like, so the initial days, you can see within the short time, you can see how much percentage of drug was released. It is pretty high. That means the moment when the drug is, administered into the patient or the tissue, the drug, most of the drugs, like around 95% of the drugs has been released. And then the remaining 5% is released for a long time. Okay, so that doesn't make any sense. The drug should not be released like this. So if it is ideal formulation or the ideal drug, how it released, over the period of time, the drugs started to release, slowly. Of course, it can be released like that. There will be a changes, something like this. You can release a little bit of drug in the initial days and then again it getting released slowly. So over the period of time, long time. Okay. So yeah, this is how the two different types of drug release phenomena usually it happens. Okay. So the reason, there will be a severe, secondary bonding, disturbance. Can be of pi interaction or the hydrogen bond interactions, etc. And you can also do the responsive release. Say, for example, if your carrier has some sort of magnetic properties or some sort of like, sensitive for lights or any other, sources, what you can do, you can also apply some magnetic environment or certain sort of light responses. You can switch on the laser light so that the drugs start to release. And if you switch off the light, or laser light or magnetic field, the drugs will not release. So you can control those things with the help of external simulations. Okay, and these are the few advantage of having burst release, as well as what are the disadvantage usually people expect. Okay, it is toxic for other tissues or the organs and wastage of drugs and difficult to predict the intensity. What will happen? Of course, if it is wound, you get treated, immediately, and you can also do the pulsatile release actually. Okay, and rest of the other stuffs like how to study the efficiency or the drug loading, encapsulation efficiency, releasing efficiency, all those things. I'll show you a couple of papers where you can, see how they are really, encapsulation efficiency, all those things they have studied. Okay. So this was one of the paper. They have used ultra fast light sensitive nanogels for cancer therapy. They have prepared the metal ion degraded nanogel, which is responsive for laser light. And then they loaded the drug into the nanogel, and then they have seen how much the efficiency of the drug and then releasing characteristics for against cancer cells. Like they loaded the doxorubicin based drugs. Okay, so I'll upload this paper as well. For the materials part, you can see the NMR characterization like to make sure that the proton, all the protons are present in the polymer backbone. And then they prepared the gels with the help of, coordination complex using iron based, cation. And you can see, the once the gel is formed, then it becomes solid actually. Okay. And then they also have studied the zeta potential and the particle size analyzer, everything to make sure that they are in the ranges of nanostructures. Okay. So you can see the particles, nanogel formations. Okay. So without sample C's, without gels like iron ferrichloride, how exactly the particle size, once the gel is started to form, how much that, nanogels, the aggregates are forming. Okay, you can see the formation of aggregate was very clear. And again, once the gel, whatever the gel formed, if you start to do the irradiation with the help of laser light, you can see how much cross-linking, the gel color is getting transformed into white. Okay. And then rheological data, like once the nanogel is formed, you can see the intensity is getting increased. That means the modulus is getting increased due to that presence of cross-linking. And now you are going to see the drug releasing characteristics. Okay. So the red color one with lasers and the sample C2, I mean, without lasers. So if we do the laser pulsated release, you can see the moment when you switch on the drug, switch on the laser light, you can see how much the percentage of drug release is getting enhanced. And if you switch off that one, and you can see the drug release was, hampered. Again, it is getting increased when the moment when you switch on the drug, sorry, laser light, and which is not the case the sample without laser light irradiations. Okay? That shows your sample is responsive for your external simulation called laser light, because the polymer they have taken, the acrylic based black oak polymer is they are thermosensitive polymers. Okay. And yeah, this was the cell viability studies. Okay. Nanogel, and then with the docs means doxorubicin based drugs. Okay. So with laser and without laser, how much cells are dying actually? So initially you can see at 0.1 concentration, the cells are almost like 90% cells are alive. The moment when you increase the concentration of gel along with the dogs, everything, you can see the cells are getting died significantly. Okay, the cancer cells. This was again the microscopic studies, how much the cells was getting died over the period of time, like 0.5 hour, 2 hour, and 4 hour. 4 hours, you can see almost all the cells are getting died. Okay? And then this was the case, like if you have those kind of burst drug release or kind of any adverse effect of those burst drug release into the other tissues or the organs of your body, you can also see. This study was carried out using a small animal called mice. They injected the drug, and then they have seen how the drug is either they are doing any adverse effect on other tissues. You can see the control samples like heart, liver, kidney, etc. There was no change as compared to control as well as the dox loaded nanogels. You can also see the morphology is retained. That means the drug was not inducing any kind of adverse effect to that respective organs. Okay. And this was the mice they used. This was the tumor-induced mice, and then this was blank nanogel, and this is dox-loaded one. Okay, once you load the drug-loaded sample, you can see the tumor sizes. Getting reduced. Actually, that means the cancer cells are getting, died. Okay. So one data is missing, the drug loading efficiency. Okay. So usually drug loading efficiency is usually studied by using UV visible spectroscopy. Okay, because every drug has some certain UV visible absorption level number. So once you load the drugs into the nanogels, what will happen? That intensity will be varied. So that area under the curve will be calculated, as well as we have certain formulas where you can see. You can read out that intensity, and then you can substitute in the certain formulas like absorbing that absorbance versus the blank one. So obviously the blank one will show higher intensity, and the loaded one shows less intensity. So with the help of that, numerical calculation, you can obtain that percentage drug which was encapsulated into that sample or the nanogels. The same thing when if you want to measure the releasing efficiency also, you keep that drug, where you want to release, maybe in the buffer solution like phosphate buffer or some other buffer solutions. So leave it for some time, like every alternative times, like 10 minutes or 15 minutes, you can take out the supernet, and then you can do the UV analysis. Again, when the time progresses, you can see the intensity will get increased because more amount of drugs will start to release. Okay. So again, that will be compared with the raw data, the standard drug intensity. Okay. Through that, you can, figure it out, like how much drug was released from that carriers. Okay, and that was a responsive release, and this one was like the drug was released using magnetic field actually. Okay, what they did again, they have fabricated the micelle. Okay, and then they have incorporated the iron nanoparticles into the carrier, and subsequently, they have seen like a drug loading efficiency as well as drug release characteristics using different, mode of release, like with respect to that thermal variation. By changing their temperature, how it is releasing, as well as the magnetic field. Okay. So rest of the other stuffs you can read. The polymer was prepared by using atom transfer radical polymerization. Okay, and subsequently the drug was encapsulated into that. This was the NMR characterization of the responsive glycopolymer was prepared, and then they have prepared different blocks which has different molecular weights. And this was a micelle they prepared. You can see the particle sizes are pretty much less than 100 nanometers. Okay, and since it's a thermoresponsive polymers, okay, what they did, they have carried out the micelle, particle size of the micelle formation at different temperatures. Okay, and then you can see like from the temperature, if you are increasing it from 30 degree to 45 degrees Celsius. Okay, you can see the particle size changes from 150 nanometer, 185 nanometers to 80 nanometers. Okay, so that was a technique again they used for drug releasing as well. Like you load the drug at 30 degrees Celsius, and then if you change the temperature during the releasing time, and the structure will start to collapse. That's the reason why the particle size or the hydrodynamic diameter is getting reduced to 8 nanometers. Once the particle is affected, the morphology, the drug, whatever it was encapsulated, that will start to release. Okay. Yeah, this was the case. Like you have a glycopolymer, micelle, and then drug was encapsulated into that, and then you slightly change the temperature, either LCST or the upper critical solution temperature. And then what will happen? This micelle will start to collapse. As a result, the once this is getting disturbed, that means the hydrogen bond is getting broken. And once the hydrogen bond broken, then the drug will start to release. Okay, as the micelle is getting collapsed. So this was a concentration of drugs which was given to the cancer cells. Okay, so if you see the higher concentration, all the cells are getting died. Okay. Yes, this was a drug release studies. At different temperatures. So you can see here the burst drug release was completely avoided. Okay, even at 3 hours, you can see the drug release percentages was only 5 to 10%. So when it goes like 20 hours, 22 hours, you can see drug release was 50% only. That means the drugs can be released for a longer time, or you can release the drug at a controlled way actually. Okay. Of course, when the moment we increase the temperature, you can see the drug releasing characteristics also pretty high, as it is a thermosensitive, micelle polymer. The same in vivo studies was also confirmed that the DOX loaded carrier is, significantly reducing the tumor size, the tumor volume. And they also made sure that it is not affecting the other organs of your tissues. Okay. Well, that's it. That's all about the your functional materials, like nanostructured materials, how to use for drug delivery sectors. Okay. And yeah, fine. This technique I missed to explain. To prepare the scaffold, you can use 3D bioprinting technique or other stuffs like freeze drying approach, or other stuffs like electrospinning, etc. So apart from that, we do have other techniques called salt leaching technique, which is nothing but you are going to dissolve your polymer or the protein in a suitable solvent, maybe a water or the organic solvent. along with the nanoparticle and other inorganic salts, okay, with specific dimensions that which are added to the solutions. You know how, first you take a I mean grinding uh, uh, grinding vessel or kind of beaker where you're going to put all those, nanocrystals or the inorganic crystals to reduce the size, okay, by with the help of different sieves, okay. On the other hand, you dissolve your polymer in a suitable solvent, say for example, polylactic acid dissolved in dichloromethane. And then once the dichloromethane is dissolved, you put your, particle size reduced to inorganic crystals, okay, or the salts into that dissolved polymers, and then you dry them out, okay. Then you get a films, and that films you put it in the hot water, okay, or in the normal water. Then what will happen when the when the moment when you put those films in the water, basically you are immersing those films in the water. What will happen? All those inorganic crystals, then sodium chloride, they will start to come out. Okay. Once that sodium chloride salts comes out, you will end up with the formation of these porous structures. Okay. So that is called salt leaching method. Once you have this kind of porous structures, these kind of foams can be used for various purposes, maybe of drug delivery applications, or can be used for tissue engineering purpose, like tissue regenerations. And yeah, that's all about those stuffs. And apart from that, how you make sure that your your nanocomposite formation is proper, or kind of your nanofiller is dispersed properly. Okay. So we do have some sort of thermodynamic concept, like or you can say like modeling of nanocomposites. Okay, this is nothing but you're going to calculate the free energy, or delta H of your nanocomposite formation. Of course, you know that for the successful reactions, your delta H or the free energy should always negative. Okay. So if whatever they're calculating, the energy of your system, if they shows negative free energy, then you can say that your nanocomposite formation is proper, and definitely that will give you the desired properties, either of mechanical or other stuff. So that means the nanocomposite formation doesn't merely mixing of two stuffs, matrix and filler. No, it's not that. So the successful nanocomposite preparation implies the proper mixing of two components in a homogeneous fashion. Okay. So that means the dispersion of nanofiller or the nanoparticle in a polymer matrix is good only when the polymer has the ability to wet the nanofiller surface. Okay. So basically, thermodynamic parameters owe their responsibility to the successful nanocomposite formation, which is reflected in the property improvement of the nanocomposite. That's what. So if your thermodynamic the parameters like a free energy or the delta H, okay, if they don't show any positive signs, that means your property will not improve at all. Okay. So now you're gonna see certain formulas, like you see the formula, like how to find out the change in free energy of the system. So E means polymer and C means composite. Okay. And you see here, once if you want to calculate the free energy of the system or the composite, then you'll have to combine the composite, the matrix as well as the filler system of your free energy. Okay. So that means delta H minus T delta S, randomness process in your nanocomposite. So that means the process of nanocomposite formation will be thermodynamically favored or the facilitated only when the delta G is negative. And this is that's possible only when delta H is negative. Of course, delta G and delta H and delta G is almost same. And delta S, the entropy should be in positive. Okay. So with the help of other combined techniques like Fourier transform infrared tool, you can calculate the either delta GS or the delta H system of your nanocomposite films, or the formation of your nanocomposite structures. Okay. So what you are basically you're going to do, you're going to measure the change in the wavelength or the wave number. Okay. how much the shifting was done to the certain functional group in your nanocomposite formation. Okay, so you see here. So this graph is FT spectroscopy of polyurethane hydroxyapatite based nanocomposites. So if you see the functional group of hydroxyapatite or the polyurethane, you have got NH2 amine groups, and you have alcohol groups, and then you do have other stuffs like calcium oxide, etc. Okay, so you have to look at different functional group and their peaks and peaks, as well as how exactly it is shifting, either shifting towards to lower WAV number or the higher WAV number, etc. Because if the peak is shifting towards to lower WAV number, means the bond, the respective bond is contributing some energy to the system to create some secondary interaction, maybe of hydrogen bond interactions. So here you can see here like this, I mean, 3,300, it is belongs to that, I mean, alcohol functional group of your this one hydroxyapatite, which is contributing for the formation of hydrogen bond towards to amine groups of your polyurethane. So of course you also have to look at the amine functional group. I mean, how much the shifting was done, okay, or the carbonyl region as well. So if they are shifting towards to lower WAV number, means that definitely they are losing some energy to induce those secondary interactions. Okay, the shifting, how much shifting was done, you will have to calculate. Okay, I mean NH2 stretching here, and you can see here the NH2 amine shifting was for the pure TPU or the thermoplastic polyurethane, which is 3,322.28, and it is shifting towards to I mean lower WAV number. I mean about 5, 7, 9, 8, etc. Okay. So once you have these numbers, I mean how much the WAV number shifting, then you put them in this empirical formula, then you'll get this delta H value or the delta G values. Okay. Of course, both if they shifting towards to lower WAV number, then you'll end up with this negative enthalpy, change in enthalpy. So negative signal always gives you the, the system that your system is, favorable. I mean, the nanocomposite formation was successful. So of course here the filler and the matrix, like you have a thermoplastic polyurethane. I mean, having the hot segment and soft segment. Hot segment has NH2 groups. Okay, and that will participate for the hydrogen bond interactions with the surface functional groups of your hydroxyapatite filler, which is nothing but alcohol functionalities. Okay. Yeah. So yeah, then you'll have to again verify or the cross check with the property improvement, maybe by measuring the tensile strength, other mechanical properties. That's how we always, make sure that the nanocomposite formation is successful with respect to that polymer and filler interaction, or the matrix and filler. So yeah, I stop here, and yeah, if you have any doubt, we can discuss. Otherwise, see you on Thursday. And I'll upload today your mid-semester corrected versions by tonight. And when is your class committee meeting? Is there any date decided?
Date they have not decided, sir. I think
Yeah.
on Thursday maybe could be there.
Okay, okay. Please let me know, huh? Soon as. Yeah, I'll
Yes.
get email also, but still. Okay then. See you Thursday, day after tomorrow.
Thank you, sir.
Yeah.